We discuss energy in electromagnetic waves or energy stored per unit volume in electromagnetic waves. Here we know an electromagnetic wave has associated electric and magnetic field, and we have learned that the energy stored per unit volume in electric field is given by half epsilon 0 E square, and we saw the energy stored per unit volume in the magnetic field is 1 by 2 mu 0 B square. So energy stored per unit volume in electromagnetic waves or electromagnetic field is given by sum of the electric and the magnetic field energy densities. So that is equal to half epsilon 0 E square plus 1 by 2 mu 0 B square. If we are considering plane electromagnetic waves traveling in z direction, the electric field we know that is given by E of zt is equal to E0 cos kz minus omega t plus delta x electric field in x direction, polarization in x direction, B of zt equal to B0 cos kz minus omega t plus delta y, magnetic field in y direction, electromagnetic wave traveling in z direction. B0 we know that is equal to E0 by C. Okay, B0 is E0 by C. So it is very clear from these two equations that B, the magnitude of the magnetic field, B is equal to E by C. Okay, B equal to E by C. Okay, so here in the expression for the B square, B is equal to E by C, so B square is equal to E square by C square, and we know C, the velocity of electromagnetic wave, is equal to 1 upon root epsilon 0 mu 0. So C square is equal to 1 over mu 0 epsilon 0. So B square equal to E square by C square, that is equal to mu 0 epsilon 0 E square. Right. So the magnetic field contribution 1 by 2 mu 0 B square, that will be equal to, since B square is equal to mu 0 epsilon 0 E square, that will be equal to epsilon 0 E square. So the magnetic field contribution is same as the electric field contribution because both are equal, half epsilon 0 E square. So U, the energy density, energy per unit volume, that is half epsilon 0 E square, the electric contribution plus the magnetic contribution, half epsilon 0 E square. Both electric and magnetic field contributions are same, they are equal. Okay, so one can say U is equal to epsilon 0 E square. E we know, that is E0 cos kz minus omega t plus delta unit vector x. So E square is E0 square cos square kz minus omega t plus delta. So this is our energy density or energy per unit volume stored in the electromagnetic wave. Okay. Now we have learned the Poynting vector. Poynting vector is the energy flux density or the energy per unit area per unit time. Okay, a Poynting vector is the energy flux density, the energy per unit area per unit time, that is given by S. Poynting vector is represented by S vector S equal to 1 over mu 0 cross product of electric and magnetic field E cross B. So S is equal to 1 by mu 0 E cross B. So this is the Poynting vector. And what is the Poynting vector? The magnitude of the Poynting vector, it is the energy flux density that is the energy per unit area per unit time. Okay, now here for electric field I am substituting E0 cos k z minus omega t plus delta x, and for magnetic field I am substituting E0 by c cos k z minus omega t plus delta y. So we will have a cross product of x and y, that is cross product of unit vector x and y is unit vector z. So that is equal to 1 by mu 0 c E0 square, 1 by mu 0 E0 square by c cos square k z minus omega t plus delta unit vector z, cross product of x and y. Now I am introducing a c both in the numerator and denominator, so I have 1 by mu 0 c E0 square by c square cos square k z minus omega t plus delta unit vector z. So this is the pointing vector, and here we know the c u is equal to epsilon 0 e square. Okay, u is equal to epsilon 0 e square. Here for c square I can have c square is equal to 1 over mu 0 epsilon 0. So as we substitute, we will get s equal to c epsilon 0 E0 square cos square k z minus omega t plus delta unit vector z. There epsilon 0 E0 square cos square k z minus omega t plus delta is the u, the energy density in the energy stored per unit volume in the electromagnetic wave. So we get a simple expression for pointing vector, the energy flowing per unit area per unit time, that is given by cu z. The pointing vector is pointing in the z direction. So we get a simple relation for the pointing vector.